Am I good to go, Paul?
Yes, you are. That looks good. Thank you.
Okay, great. Thanks again for the intro. It's really great to be here to participate in this fantastic MLCAD program. Today, I'm going to talk about some of our recent research results on applying ML to improve agility and also efficiency of hardware design. Actually, in my mind, this is probably one of the most interesting times, right? Most exciting times to build new hardware. First of all, the demand is very strong, right? There are a wide range of applications which are very compute intensive, and they need to run fast. And not only that they also need to run in a green fashion. So for the time being, right, in the short term, right now the most obvious, also viable solution is to build new specialized hardware targeting certain application domain. This is really the first point, right? The demand is really high. And also the second point is, with this availability, also the increasing popularity of the cloud FPGAs and some of the open source hardware ISAs and hardware IPs, it's probably, the technical barrier is probably lower than ever for a team to start building new special purpose hardware. Along this direction, it's really fascinating to see some of the giant companies, right, in software industry or even automobile industry. They are starting to make their own chips, right? They're starting to build their own hardware accelerators. This is the bright side. Right? On the flip side, there's always a flip side. We can also argue that this is probably one of the most challenging times to build new hardware because the target of specialization is moving very quickly. It's already fairly well known that you look at the ML field alone, right? So the number of papers being archived is actually increasing at exponential rate, even faster than Moore's law. And also within our community, there's also this very well-known gap. It's actually a widening gap between the so-called technology capability promised by the Moore's law and the actual hardware design productivity. So if we really put these two plots side by side, the trend is kind of worrisome. So why is it? Actually, this is, I guess it's fair to ask the question, right? Can we build this custom hardware fast enough, right, to keep up the pace? If you look at the traditional or also the mainstream design flow, we start with HDL. We go through synthesis to design, and in many cases we have to do gate level simulation to do the close timing, also power. If you look at this traditional flow, it's actually fairly time consuming, right? It's extremely painful in many cases to just do one design iteration. It often takes hours or even days, right? Just to iterate once and then modify design and then keep iterating. So this is where the design productivity really drops. With the introduction of HLS or high level synthesis, right? Actually, it certainly helps, right? It certainly helps to get to from concept, right? Design concept to RTL or HDL faster. Ideally, the hope is that we can make use of HLS compiler and then quickly explore a much wider range of design points, right? So per iteration with HLS may only take minutes. So this is the hope, right? But if you look at, there's a catch. The catch is, although this iteration cycle is fast, but at this high level design stage, we often have to rely on a very crude and very inaccurate QOR estimation. QOR here stands for quality of results. Right? So basically, this is our dilemma, right? There's this strong tension between the speed of the CAD tool and also the fidelity of the QOR estimation. This kind of tension actually exists across the whole EDA or CAD tool flow, and this is something that we have to address to enable agile hardware design. To some extent, right, machine learning ML is sort of becoming one of the key enabler, right, for building new hardware designs, and it's also introducing many more challenges, right, in terms of design productivity. It's also tempting to ask, can ML also become one of the part of the solution, right, to cure this design productivity issue? There are actually many interesting opportunities, right? For example, ML is really good at approximating functions, right? Can we make use of ML, can build some ML model to act as like a glorious function approximator to better estimate the quality result, to better estimate delay, power, and area. And this is one opportunity, right? And also ML has been shown to be useful in many design decision-making tasks, right? Can we here make use of ML to enable more intelligent hardware design and also further optimize the CAD optimizations. That's another obvious opportunity. In my group, we actually have published quite a few papers. We've been exploring both directions. We have been using ML to improve the estimation, QR estimation for HLS. We also look at the congestion prediction for FG designs. This is for the first part of the QR inference. And for the second topic, we also make use of ML to do parameter tuning or auto tuning for CAD tools. And also, we're starting to use ML to apply to circuit synthesis. I'm going to mention some of. I'm going to talk about some of this work in more detail. But of course, there are also other related work, right? This is a fairly active field, right? There are a lot of interesting and new work emerging in recent years. If you look at many of these, right? So quite a few of them focus on improving this QOR estimation or QOR inference. Actually, again, there's this kind of right there's a tension between speed and fidelity. So this exists across the entire design flow, and also there are many who are looking at how to further optimize the circuit generation and also how to speed up the design space search. Also, there are very promising work on accelerating the CAD algorithm itself by casting certain time-consuming CAD two-step like placement, right, as a ML training problem. If you look at, although there are many promising results right in this area, but if you look at many of this work, they actually face similar challenges, right? Because ideally, we want to build this so-called design agnostic learning model, right? So that we can build this, magical model where we can predict QR, let's say, right, for any kind of design, right, with high accuracy. But in reality, right, although this would be ideal, right? But in reality, right, in many cases, we have to do supervised learning. We may not have in many cases, we actually lack the established data sets. Right? There are actually very few rules design available, publicly available. So there's really no image net equivalent in our field, right? Like a circuit net. So even if we have even if we have a lot of designs available, we still need to do this data collection. We still need to do the pre-processing of the data. Right? This process itself is also challenging because like I mentioned, the CAD2 flow, the CAD tools are extremely slow in many cases. It takes hours or even days to compile. So even with these many designs, right, we may not be able to quickly process the data, clean up the data to generate a meaningful data set. And even if so we have the designs, we have the data cleaned up, it's still fair to ask the question, whether these designs indeed form a sort of meaningful distribution, right? Can we actually make use of ML to learn something useful from a variety of designs if they are indeed available? But in many cases, the generalization is difficult according to our experience, because many different designs from different domains, they may have very distinct, very different characteristics. They may not even form a meaningful. We may not be even learn anything useful from this set of benchmarks or designs. So these are the obvious challenges, right? So having said these, maybe it's useful to take a step back and then look at design or domain specific learning, okay, instead of just focusing on design agnostic learning. It's actually useful to point out that if you look at digital hardware design, there's a rich source of information available across all different design stages. These are the traces. Right? When we build digital hardware, we run waveform to simulate. Right? So at gate level, RTL level, we have a lot of traces available. And cycle level, same thing. We have the transition of the stateful signals. At even higher level, like functional level or transaction level, we also have a lot of traces available, right? That are ready to use, like the activities at the interface. The research question here is, can we make use of these traces? Right? These are much ubiquitous, right, in our design process, and in many cases, these traces indeed hold and show very useful information of the. In many cases, traces have more information than what we can get from static analysis, and also these traces are often hard to parse and analyze by human. But might be easier to analyze by ML. Okay, this is the hypothesis. In the rest of my talk, I'm going to focus on two topics. So both are related to trace-based learning. First, I'll show you how to do trace-based learning for QR inference. And also, after I'll talk about, we can also do trace-based learning for circuit synthesis as well. For each one of these topics, I'll focus on one of our recent papers. I'm going to start with Primal. This is a trace-based learning technique for power estimation. This is joint work with my student Yuan and also our collaborators at NVIDIA Research. Okay, let's talk about Primal first. Again, this is about power estimation. Needless to mention, right? Power estimation is really important for modern day hardware design. Right? We really care for energy efficiency, so we do want to have accurate estimation of the power consumption. And the thing is, in many cases, especially for ASIC design, right? In order to sign off a design, we have to do accurate gate level power analysis, right? Which is extremely slow. Just to give you some concrete data, right? You want to simulate a 5-stage pipeline RISC core, this bit in order pipeline processor. It's not a big design, but at gate level, if you want to do power analysis, we can only simulate up to 45 cycles per second. This is simulation speed, which is painfully slow. Right? To translate a little bit, so that means per day, right, we can actually only simulate less than 4 milliseconds of the processor time, which is really awful. Right? So ideally, if you can actually simulate the whole design at RT level, we'll get a much higher speed up. But it's not that easy to get accurate power analysis at RT level. Right? We just focus on the dynamic powers, the switching power. It's not that easy to accurately estimate many of the factors. Right? If you just look at capacitance alone, we have to look at different things, right? Standard cell parameters, gate size, invariance, and such. It's not that obviously this is a challenging task. But still, it's useful to ask this sort of question. Also state an ambitious goal, right? Can we make use of ML, right, to achieve gate level accuracy, but at the same time achieve the speed of RTL simulation? Okay, is it even possible? So argue that if you focus on design-specific learning, right, if you focus on a reusable ASIC IP, right, this goal might be realistic. So here's our flow. When talk about Primal, right? Primal means power inference using ML. What we are trying to do is for a given ASIC IP, okay, again, this design specific. Usually we have a set of verification test benches. Right, these verification test benches. This is just for verifying the correctness of the function. Right, this can be unit test cases or can be even like synthetic random stimuli. Okay. We'll try to make use of these test benches and run our estimation. And we also go all the way into gate level power analysis. So with this data, with these traces, we use them to train an ML model. Okay, this is done once per design, right, for this reusable IP core. And once we have this ML model trained, that's where we can start doing the inference, okay, using the realistic user test benches. Okay. Basically, we train the ML model, okay, using the gate level estimation. We run it for a certain number of cycles, but hope that this ML model is accurate enough so that once we start the real test, right, we start run the interesting test benches, we can run it and then get accurate power estimate and run it for many, many more clock cycles. Hopefully this makes sense. And also this gives us a much higher speed up, right, compared to gate level estimation. So this is what we are trying to achieve. Of course, it's important to encode, right, the features, right, for ML to have the right features for training ML model. So over here, actually, it's not that hard to come up with a set of features when we run the RTL estimation. One way is to do the so-called 1D encoding. Over here we're trying to do a cycle by cycle power estimation. So all we are doing is we are encoding, looking at the switching activities of these registers in the RT level, and per register, also some other signals. We basically look at per clock edge, right? Whether it's switching or not. If it's switching, then we encode it as a 1. Otherwise, we encode it as a 0. So basically, for each clock cycle, we have basically 1D, right? So one-dimensional vector. And then this is basically 0, 1 vector. That's how we can get the training samples. We have 1 training sample per cycle. So this is 1D encoding. In some cases, it's actually also useful to do 2D encoding, especially when we use the like CNN models when we train a CNN model to do the power estimation. So it's a 2D encoding. Over here, we are also looking at these RTL registers and also some intermediate signals. Over here, but instead of doing a 1D, instead of just packing everything into a 1D vector, we instead pack it as a 2D image, right? Each pixel basically corresponds to a register. So that's sort of the mapping. And also with this 2D encoding, we can also leverage some of the existing, just similar to how a CNN process image. We can also create per sample or per cycle, we can create 3 channels for each image. So in this channel, the first channel means whether certain, we look at each register. If it's not switching at all, so we put a 1 there. Okay. Otherwise, if we have a rising transition, right, from 0 to 1, we put a 1 here for that corresponding register. And this one basically corresponds to the falling transition. Okay. Again, this is basically one hot encoding, but encoded in a 2D form. So these are how we collect and also encode the features. With these features, then we can apply the ML. Right? We can for 1D feature representation, we can just use some of the traditional ML models, like some linear regression models or also tree-based model. We also can use a PCA to do the dimensionality reduction. With the 2D feature recognition, we are trying CNNs. When we did the research, we basically used this efficient shuffle-net V2 model to do the training and power inference. Okay, so to show you some results, if you look at the cycle-by-cycle estimation accuracy, over here we measure the error by this RMSE, normalized RMSE. We look at several different designs. Some of those are simple blocks, arithmetic blocks, like multiplier and floating point adders and floating multiplies. We also look at NOT router and also RISC-V core. So on average, with these ML models, actually, pretty much all of the models perform well enough. On average, the error is less than 5%. With the CNN-based model, it is a more complex model. We are getting even lower error, so less than 3%. So this is cycle-by-cycle estimation accuracy. We also look at the average power estimation accuracy. So this is where we compare with a commercial RTL power analysis tool. Over here, you can see that indeed, for some of these designs, even the commercial tools is not really giving us a very accurate prediction. But since we are doing this design-specific learning, right? So with these ML-based techniques, we can get a much higher accuracy. Right? On average, it's error is just less than 1% for the average power estimation. Also, we took a zoom-in view, right? For some of the designs, we look at this RISC-V core. We look at the dry stone benchmark. We actually look at these cycle-by-cycle traces to see how closely the prediction is matching the ground truth. Over here, the ground truth is basically produced by the PTPX tool. These are 2 different models, right? Over here, this is a simpler model where we are doing PCA-based dimensionality reduction followed by ridge regression. And over here, we are using CNN, right? This is shuffle-net V2. You can see that indeed the predicted power trace actually match pretty well with the ground truth. And the CNN model is indeed matching. It's actually closer, right, in terms of the prediction. The gap between prediction and the ground truth is indeed closer than a simpler model. Okay, so this is accuracy, right, in terms of speed up compared to Synopsys P2PX. On average, we can get 50x speed up with CNNs. right? With a smaller error, with simpler model, we can get even higher speed up, right? But with slightly higher error. So there's this trade-off. Okay. Hopefully this makes sense so far, right? This is primal. So there we are using RTL simulation, and then we feed the trace RTL traces to power inference model based on ML, so to do the prediction. Turns out that we can also further elevate the level of design abstraction. So if the design is generated or synthesized by HLS, we can also make use of the traces produced by some HR simulator. So over here, we are using a simulator called Flash. This is a transaction-based cycle approximate simulator. In the interest of time, I'm not gonna delve into details here, but what I'm gonna mention here is that so similar technology, similar approach, similar methodology also works for HLS general design. We can get even higher speed up, because we are running at a higher abstraction level. But with this kind of simulator, the hydro simulator, we do need to account for some of the cycle shifting behaviors since it's a cycle approximate. And that's where we found that using LSTM-based model actually give us a higher accuracy. Okay. Again, I'm not going to get into details. I'll later show you a reference if you're interested in learning more about this work. All right, so this is primal. Okay, so this is how we apply ML to do trace-based learning for power modeling. In the second part of my talk, I'm going to focus on synthesis. So it turns out that we can also use trace-based learning to generate some smarter hardware for decision-making in computer architecture. The primal work was published at DAC 2 years ago, and this new work is going to be presented at DAC 2021. This is also joint work with my student Yuan, and a business student Han Yu, and Professor Jieming Yin at Lehigh. Okay, so here's the context of this work, this research. So there are actually a lot of opportunities in architecture design automation, since if you look at the modern day computer architecture, there are many decision-making tasks, right, which are currently relying on simple human design policies or heuristic. For example, we are doing prediction, right? A lot of prediction in the computer architecture, whether it's run prediction or prefetching, or resource management like arbitration, replacement, or QoS regulation, right? Like DBFS. So these are all design decision tasks. So right now, many of the existing components, right, in the computer architecture, they are using simple heuristic, which in some cases can be ad hoc, or in some cases cannot really exploit design-specific characteristics to achieve high performance. So this is where there's this obvious question again, right? Can we apply ML? Can ML play an important role in terms of automating some of this decision-making process? There are indeed actually some recent work showing pretty cool, pretty promising results. Many of them are using DNN-based models. For example, there's some work that apply LSTM to do prefetching, and also some work that apply RL, reinforcement learning, to do some arbitration-related work. But most of this work actually right now were reported. Most of the results were reported in the simulation settings. It's actually not that clear if we can implement the learned models in this work using efficient hardware. So just to make things more concrete, right? Let's just focus on arbitration. Let's say we focus on NOD or NOC packet arbitration, and give you more details here pretty soon. Okay. If we do arbitration, so over here in actual hardware, we are dealing with a very tight delay and also area constraints. We have to make decision, right? In 1 or 2 cycles. In many cases, we have to use a conditional logic, right? So that we can quickly decide which packet to choose in just a single cycle. And also, we cannot really introduce too much area overhead. Right? We look at simple router. Based on some of our experiments, if you just take a very simple router, it may only use this much area. It's a 4,000 square micron. So that pretty much rule out, right? The option of using a dedicated deep learning accelerator. Right? That's just too big and too slow. If you just move the data alone, that's going to kill the performance. And also the whole, right? The accelerator is going to be too big to fit in in context like this. I just mentioned the area constraint, right? What if you do not use a dedicated or programmable DNN accelerator? What if you use a hardwire, let's say hardwire MLP, basically hardwire dot product array? That's also not small enough, right? Because this is the area constraint over here. Based on our experiments, right? Just if you just use one 8-bit multiply, it already consumed this much of area. Really, and there's not much room to add more multiplies or additional adders. So these are the challenges. So to sort of address some of these challenges, we are looking at this the circuit distillation problem. We are actually proposing again a trace-based machine learning methodology. So this is where we are trying to make use of RL or reinforced learning to learn a DNN or MLP model from the simulation traces. So this is based on supervised learning. And once we have the DNN model, so we'll try to distill it to some model distillation to a simpler tree-based model. And this tree-based model can be further regularized and optimized, where we can generate a very efficient conditional logic. Right now, we are mainly focusing on arbitration logic, since this actually turns out to be a very good fit for this kind of flow. Since, like I mentioned, we are dealing with a very tight latency constraint, so that's where we need conditional logic. And also, in many cases, look at those arbitration logic, the input bandwidth to the circuit is usually relatively low, and also the output is usually a priority score. So that's a good fit for ML, right? So where we can do regression or classification. Okay, this may sound too abstract, but again, let me show you a very concrete case study. This is a NOC router. Again, this is where we look at the on-chip network. We are looking at the fair standard virtual channel-based flow control. We are using VCs. Right? Basically, each router has static buffers for these virtual channels. I'm not gonna get into details over here. So, these are fairly well known. So what we are focusing on is this so-called switch allocator. So that's where we are making choices. We are choosing packets from different virtual channels, and they're going to be arbitrated for certain output ports. And this is actually interesting and turns out to be very important decision-making process for the NOC router. Again, I'm showing you this diagram. Right, this is a abstract diagram. I'm going to show you a concrete one pretty soon. What we are dealing with is we have this arbiter, right? We want to choose between multiple packets from different virtual channels. And in the end, we pick the one with the highest priority. There are many different kind of policies that we can consider. The well-known ones, also the well-established ones. We can use a very simple round-robin based approach, right? Or we can use a first in, first out, right? FIFO-based approach, which basically just consider local age of the packet. Right, so basically, we look at how long certain packet has stayed in the specific certain router. Or we can use a Oracle approach, Oracle policy. This is called GA or global age. So this is where we look at how long certain packet has been bouncing around in the NOC. Okay? This turns out to be a very good policy, so that's where we use it for Oracle. But this is very hard to compute in general. And also, there are some manually or handcrafted policies. So one is from actually our collaborator Jianmin Yin's work, the HPCA 20. So there, he actually trained an ML model, but he doesn't really have a way to fully automate the synthesis process. And he tried to basically distill the model by hand to generate some handcrafted policy. Okay. So what we are trying to do is we want to automatically learn this policy, okay, using ML. This is the diagram of the switch allocator. Again, we have these virtual channels, right, set of VCs. And for each packet, we consider a few features. Okay, we look at the local age, basically how long this packet has stayed in the current router, and the size of the payload, and also hop count. Hop count means how far this packet has traveled in the NOC. distance means how much further does the packet has to travel to reach the destination. So in the end, it generates this arbiter or arbitration logic generate the priority score, and the highest one get chosen, and then we will go to the corresponding output port. Okay. What we want to do is we want to replace this this arbitration logic with some MLP-based agent. This is automatic train and learn. Okay, so this is the setup. What we are doing is we are using RL. Okay, we are using reinforcement learning to train this MLP agent. Again, we do a trace-based learning technique approach. So where this is submission setup, we are using Gen 5, we are running Gen 5 to get the traces. We are simulating a 4x4 mesh network. Okay, so this is actually very much similar to this repeatable HPCA 20 work. We are using Garnet. This is the NOC simulator integrated into the Gen 5. We are using the uniform random traffic with an injection rate of 0.32 to train the ML model. Okay, and we are using deep Q learning. Okay, this is the setup of the MLP. We have one hidden layer with 16 neurons. The key here is that we are using this so-called Oracle, right, the global age policy to train the model. So if the MLP, if the learned model is giving the same prediction with the Oracle, then we give it an award. Otherwise, there's no award. So that's how we train RL. Here are some results. Okay. We look at the training process. Okay. Basically, these are we train for this many episodes. The orange line is the Oracle. You can see that indeed with RL, with reinforcement learning, the MLP agent is learning something useful. It's actually gradually converging to the the best possible policy. Okay, so these are the other references. Right? Indeed, actually this is at the injection rate of 0.32. We are using the same setting of the training in this case. Indeed, the RR means round robin, and FIFO, they are much worse in terms of latency. But again, this is just the MLP, right? We get the MLP, but how can we actually implement it in the real circuit? So that's the challenging question. So over here, we are doing this so-called model distillation. So where we translate the DN model or MLP into a tree-based model. To make the tree much more friendly for hardware implementation, we further to regularization, we constrain the size or depth of the tree, and also we quantize the weights for the so-called linear model trees. I'm going to introduce this pretty soon. So both techniques basically make trade-offs between the accuracy and the complexity of the circuit. Okay, all right, so here's an example. We try to distill the trees. We look at two kinds of trees. One is this vanilla, right, decision trees. Basically, at deep level, we have these scalar values, right? So these trees can be easily implemented into hardware, right? So using muxes. Also, we look at another variant of the tree model. So this is where at the leaf level, we have these so-called linear functions. This tree model is called linear model tree, or LMT. Once we distill to this kind of a tree model, we also do quantization so that all the coefficients are power of 2, which is very friendly for hardware. So we don't need to spend any, we don't need to use any multiplier resources. Instead, we just need to do shift. Okay, so that's how we generate the tree models. Here's the actual result, right? With the tree-based model. I showed you the MLP-based result, and this is the one with the real circuit, right? Basically. Okay, maybe let's focus on this table first. Okay. This table shows the performance area results of the distill circuit, the learn and distill circuit. So these are the baselines, right? FIFO is basically considered local age, and this is the manual policy in the performance manual policy in the setup, and also this is beta golden, right? The one that we try to achieve. This is the Oracle. So indeed, you can see that there's a wide gap, right, between the Oracle and a simple policy like FIFO. The interesting results are over here. Like we have this LMTs, right, linear model trees. If you look at this row, So with LMT of depth 1, we can already get very average latency for the packets. Right? It's already approaching the oracle at the cost of this much of area. Okay, so to make it somewhat intuitive, right? Each adder, if you look at the 8-bit adder, right, in this TSMC 28 technology, so each adder consumes about 17 square micron. So basically, what we generate is roughly just three 8-bit adders, as small as that, and we can achieve but at the same time we achieve a very good latency. This is another plot where we show that the learned circuit actually performs indeed quite well under different injection rate. Of course, initially when the injection rate is low, basically there's not much traffic in the network. All this different policy, they are pretty much performing relatively similar. But if we further increase injection, you can clearly see the gap is widening, right, between the simple policy and the learned policy. Okay, and this is another interesting that I want to quickly mention. Okay, with this tree-based model, right, we can actually look into what exactly is being learned by RL. Also, this is basically after the distillation, right? We compare this with the manual policy proposed by this HPCA 20 paper. We look at manual policy, actually put the heavy emphasis on the local edge and also the distance that had traveled so far in the hop count. With the learned policy, this is of course slightly more complex, but it's also somewhat more intelligent. It actually considered the distance that has traveled so far, right? The packet has traveled so far. If the distance is relatively low, then it put the heavy emphasis on the size of the packet. Otherwise, it put the higher emphasis on the lower emphasis on the size of the packet and higher emphasis on the distance. Basically, it sort of represents the edge, right? The global edge to some extent. Okay, these are the key differences. We found it actually pretty interesting that with the tree-based model, we can indeed interpret what the RL agent is trying to do. Okay, just one more plot. Okay, with this, we actually train this RL, right? So with the MLP agent using this uniform random traffic, we want to also check whether it indeed also generalized to other traffic pattern. So this is where we test this different pattern called the transpose traffic pattern. So basically, with this traffic pattern, for the coordinate x, y, we send packet to yx. So basically, send to this how we basically, it's like a transpose matrix. Turns out that with this traffic pattern, even though it's not really trained, right? We did not train on this pattern. The learned policy still generalized pretty well. This is if you look at this part, right? The LMP, again, this linear model tree. So with depth 4 performs pretty well. It's very close to the global edge and also the MLP base agent. And the simple policy, again, are not doing that great. All right, just to quickly summarize, this is just one of the case studies, right, where we show that with this trace-based learning, we can actually learn very efficient combination of arbitration logic, right? In this case, for not arbitration. We are just scratching the surface here. We are training on a relatively simple network, but it's actually pretty surprising that the gap between the simple policy and the learned policy is actually pretty large, right? Even for a small network that I showed you, 4x4. And also we show that the combination of RL and this tree-based model seem to be pretty effective, right, for generating the conditional logic. And there are many interesting things that we can explore, right? We are actually running larger and more lucid network. Of course, the simulation time will be much longer, so this is one of the challenge. Okay, and also we are looking at how to do sequential logic, right? Not just the conditional logic. And also I want to point you guys to AWS. Actually, AWS, the workshop in the recent years, in the last 2 years, they have been running a very interesting context, which is basically right along the line of generating efficient logic using ML technique. Okay, so just wanna conclude, right? In case you are interested in learning more about some of the topics that I mentioned, I invite you to check out this thesis, the PhD dissertation by my student Yuan, who recently just graduated. In this thesis, he actually showed that he talked about primal circuit distinction. He also showed that there's a trace-based learning technique also applies to HLS, where we can generate highly efficient banking logic for specialized accelerator as well. So indeed, we feel that this trace-based design-specific learning can be a useful technique for many different design automation tasks. With that, I'm pretty much done. Thanks for your attention. I just want to give credits to my students, also the sponsors. I'll be happy to take questions if there are any.
Thank you very much, Zhiru. There is one question on the chat line. A question on primal. Even for some RTL, gate level net lists varies based on clock timing constraints and could be low VT or high VT dominated in term affecting power estimation. How do you take timing constraints into account in your ML code?
Right, so yeah, this is a great question. Again, we are right now focusing on design specific learning by design over here. We basically constrain ourselves, right? So once you have a specific timing constraint, so for different timing constraint, we consider there are different designs. So once we have a fixed timing constraint, once a design is sort of getting to a good shape, right? So that's where we can start do the gate level power analysis, right? Gate level sign off. Okay, so that's where the primal becomes useful. Right? So we can basically train the model where the model basically learns different parameters like the low VT, right, high VT settings, and also some of the clock gating. And after that, we can run primal for many more vectors and see whether there's any anomalies. But if there's indeed an anomaly, there's a spike, that's where we can focus on that region and then invoke the actual gate level power analysis to debug it. So that's how we envision how we can use it.
Would that also work for clock gating? Because clock gating can make a big difference in power consumption.
Yeah, indeed. Actually, I showed you some results, right? So where some commercial power analysis tool is not doing very well, right? On the average power analysis, turns out that tool is not considering power clock gating for that specific design.
Okay, thank you. There's another question here. You can probably see it now. NOC routers typically have tight area power budget. Can you briefly talk about the power area overhead feasibility of this ML-based approach?
Yeah, this is also a great question, right? So that's why we focus a lot on generating very lightweight computational logic, right, using the tree-based model. I think I showed you some results, right, using this shallow LMT or linear model tree. The learned arbitration logic is basically only using like 3 8-bit adders. That's very small. Of course, there are also other overhead. We do need to consider some additional features, right? I mentioned that there's a local edge, although in many cases, right, the existing router may already have a local edge, and we also need to encode the hop count. So those may add overhead of the packet, and they may also increase the size of the circuit. But from our analysis, those are not major overhead at least, right? As long as the learned model itself is small enough.
Thank you. I have a global question. HLS has been very successful in the FPGA domain. I've got a project using it myself. And part of the reason for that is that the resources are specified. So you can target the HLS bit easier to the domain. What do you think is potential for HLS in the standard cell ASIC domain, and will machine learning help there?
Yeah, this is an interesting question. So just want to clarify, Paul, you're talking about using HLS for ASIC, right?
Yes.
Yeah, I think HLS also, right. So you're right. So HLS is becoming really popular in the FPGA domain, right? Part of the reason that indeed there we are generating an application-specific starter for FPGA, and also the concern, also emphasis on verification is probably less, right, than ASIC. Right? One of the challenges of applying HOS for ASIC is how can you make sure that indeed what HOS generate is functionally equivalent, right, to the original design. So that's one of the key challenges. But on the other hand, at least based on my experience, many people also find that using HOS can improve the design verification, if not the formal functional verification, right? Because with HOS, you can run a lot more test vectors, right? You can run a lot more tests, right, compared to RTL simulation. So that's one of the key considerations. The other thing, talking about ML, like I mentioned, right? So with HOS, ideally you want to use HOS to do fast design space exploration, right? To design ML starter. Again, even in ASIC, I think for ASIC design, HOS are getting popular because for many starters, right? There are so many different design choices. You do want to, have this very fast iteration instead of doing the RTL level, right? Tweaks and hacking. But the challenge is that can we get good estimate, right, at the HOS level? So are we actually, when we find a promising design point, we look at the report from HOS. HOS may say, okay, this is indeed the promising design point in terms of area, power, and timing. But do they actually correlate with the result after place and route? So this is one of the interesting challenge.
Okay.
There are different approaches, but I think this is where ML can be useful.
Okay, thank you. There's a follow-up question on the chat. Another question on primal. In case of multiple clock domains, how does 1D encoding work?
Yeah, this is a great question. We haven't considered this yet, although because right now we are focusing on basically these sort of reusable IP blocks, right? We are not trying to use primal to predict power for the entire chip, but I think this might be possible in some cases, right? Basically we just have to add additional vectors, right, for the different clock domain. Right?
Okay.
That's just one brute force extension. Again, we haven't really tested this part, so my guess might be off.
Great. Well, thank you. That completes the questions. Thanks very much, Zhiru. We really appreciate it.
All right. Thank you very much. I guess I just have to go to the